what we want to look at today is basically conservation of angular momentum first, and then stability analysis. So let's look at angular momentum. And angular momentum is very similar to linear momentum. When we looked at linear momentum, you saw that the rate of change of linear momentum is very similar to Newton's second law, that mass times acceleration equals to the forces. And we'll see that for conservation of angular momentum is very similar to that. So we will see that the rate of change of angular momentum is due to the net torque that is applied to a body. And in classical mechanics, angular momentum, let me put this as a side note. So in fluid or in continuum mechanics, sorry, we look at these parcels and the body, and now we want to know what's the angular momentum of that body around an origin, let's say here, around the origin at 0. And that has to do with its position vector, r. In classical mechanics, or point mechanics, a point, basically the angular momentum of a point would be defined often as capital L is equal to R, and then the cross product with its impulse, m times velocity. So that would be the definition of angular momentum for a point at the distance r from the origin or our reference point. And we measure it around that reference point, the angular momentum. That's how you would define it. So you see the impulse or the linear momentum, m times v, and then the cross product with its position. Oops. So think of the origin, the vector to the point, and then the point can move with some impulse mv. And L again is a vector. So that would then point maybe something like in this direction. That would be angular momentum. That's how you define it in classical mechanics. So what we do in continuum mechanics is just define it the same way. But you see, mass always becomes this integral over the volume. So this body has here a volume V, which can change with time. And what we want to look at is the total angular momentum. Now let me move away this little note on the side. Which now becomes the volume integral of the density rho times this cross product of R V. So we have V is the velocity of that little volume parcel dV. R is its position vector with respect to an origin, let's say at 0. So that's how we define the angular momentum in continuum mechanics. So the total angular momentum of this volume that we look at is this volume integral. Density times the cross product of R times V. And so the rate of change of total angular momentum is equal to the net torque. And what's now the torque that we can apply to that body? And the torque we separate again into a volume and surface component. So there can be a volume torque, which is the torque which is induced by the body forces F. And there's a surface torque induced by the surface, acting on the surface sigma of this cross product of R times T, and T is the traction. As dV, T sigma. So F is like from the previous conservation model. F is the body force. And small t here, that's the traction. If you remember from last time, traction is related to the stress tensor. So traction T is the normal dotted with the stress tensor. Good. Let me remove here classical mechanics. So now we can express the conservation of angular momentum with these terms that we just wrote down. So let's look at the rate of change. Of angular momentum. That's our dO dt of the total angular momentum we have above. So the volume integral rho r times v. That's the rate of change of angular momentum, which is equal to the net torque that is applied to the body. So it's equal to the volume torque plus the surface torque. Plus the surface torque here. Good, that's how we can state the conservation of angular momentum. If you want, you can also think of Newton's second law. So F is equal to mass times acceleration. Here it's very similar. So if you look at the torque, it's basically the force, the cross product of the force with its position vector r, like the lever. So if you look at the cross product, this lever with the force is equal to this lever times the rate of change of the impulse, the momentum. So let's just state here in words. So the rate of change of angular momentum equal to the net torque. Do you know what the units are of torque?
Newton meters?
Yes. So think of torque as being this cross product R times F times the force. So it's the units is basically the Newton meter. And if you look at the rate of change of angular momentum, it must have the same units like the torque. Good. Let me get rid of that. So let us rewrite a bit the rate of change of angular momentum on the left side here. So this d dt, the volume integral R times V. So let's take that derivative again inside, like we saw from last time, conservation laws. So we keep the volume fixed and we can take the derivative inside and then end up with a flux term, how much of angular momentum would move in or out the surface. And this surface term with the divergence theorem or Gauss theorem, we rewrite as a volume integral. And then we can basically put everything under one volume integral. So we can rewrite it as the time derivative of rho r times v plus the divergence of this r times v, and now the dyadic product with v. Sometimes we just don't write this thing here. So we just write v basically. This will again be the dyadic product between two vectors, or the tensor product if you want. Okay, let us rewrite this again a little bit. So what we can do is we rewrite this as r times v times now the time derivative rho plus the divergence of rho v, and the terms we still have is rho times time derivative of r times v plus the velocity times the grad rv. And then dv. It's just rewriting these terms a little bit. But now you see that in our brackets here, this term might look familiar. And you would have to look basically at the first conservation law we looked at. So this here is conservation of mass, where we see the continuity equation, which states that this is equal to 0 in order to conserve mass. And for this part here, you would look at the material derivative, how we defined that. And so having a time derivative and then this product of V times grad of something, the quantity. That looks like the material derivative of that quantity. So what you can do is basically rewrite this part. This is equal to R, the cross product of rho, times now the material derivative of V. So this capital DT, that's the material derivative now. Good, so you see that this expression simplifies a bit. And what we also need to still do is basically look at the surface torque. That's this integral over the surface. So let's convert that into a volume integral. And then we're almost set. So let's consider the surface torque. Well, we have this surface integral of R times the traction. And so traction is defined in terms of stress tensor and dot stress tensor. And now comes a bit a complicated expression when we want to rewrite this as a volume integral. So we can use the divergence theorem, but there are terms that arise due to this cross product. And so what we have is then a volume integral of R cross product with the divergence of the stress tensor. Plus additional terms now, which arise due to taking the cross product, these two vectors. And in a very short notation, we can write it as this epsilon, the double dot product with the stress tensor T, and then we integrate over dv. So what is this epsilon hat? You see it has 3 bars below. So it's a third order tensor that we use. And it's easier, for example, you are probably familiar with the Kronecker delta. That's delta ij, defined as being 0 or 1. 1 if I is equal to j, and 0 else. Now this epsilon is very similar to the Kronecker delta, but has 3 indices. Not just I and j, but has ijk. It is called the Levi-Civita tensor. It is epsilon ijk, and is defined such that it is 1 and ijk are even permutations. Zero if some of the indices are equal. So either I is equal to j, j equal to k, or I equal to k. Then it's 0, and -1 for odd permutation. What do I mean by even permutation? So we quickly make an example. So even permutation, that's if I, j, and k would be, for example, 1, 2, 3. So I, j, k go from 1 to 3. And if we have I equal to 1, j equal to 2, k equal to 3, that's an even permutation. Another even permutation would be, for example, 2, 3, 1. Two permutation, or 3, 1, 2, for example. Also an even number of permutations of these indices. Odd permutation, an odd number of permutations would be, for example, ijk. I have here is 3, 2, 1, for example, 1, 3, 2, 2, 1, 3, for example. Those would be odd permutations. So why do we introduce this tensor, this Levi-Civita tensor? It's because the cross product can be written in a very convenient way with this tensor. So the cross product of two vectors u and v. If is another vector, and if we look at the I component of that vector, we can write this as our Levi-Civita tensor, epsilon ijk times uj times vk. So again, we have repeated indices here. So this is basically sum over j, sum over k, times now our Levi-Civita tensor. So let's get rid of these summation symbols. So we can write this cross product in a very convenient way with this tensor. That's why it shows up now when we look at the surface torque and rewrite it to have a volume integral. Good. Shall I leave you that little excursion here with these tensors? You see, what we can do now is we rewrite the conservation law, basically, the rate of change of angular momentum. We see that we can simplify the left side and then have the right side under one volume integral. So we can write everything as under a volume integral, which is valid for any volume, which then again means that we can just consider the terms inside the integral expression. They have to be the same. So let's do that and bring it a bit to one side. So it follows that we can rewrite the rate of change of angular momentum then becomes this cross product of R. Now we have rho and the material derivative of V. Then we bring over the divergence of the stress to the other side. So we have the divergence of stress minus. Bring over the body forces. And are left with, on the right side, is our alternating tensor, the double dot product with the stress tensor. So we just took the divergence of the stress on the other side, plus from the volume torque, the body forces, and then left with our alternating tensor, the Levi-Civita tensor times the stress tensor. And again, this is why we wrote it in this way. So look at the expression in the bracket. It should ring a bell from last time when we looked at linear momentum. So that's basically conservation of linear momentum. So it's equal to 0. So you can look it up in your notes from last time. So what are we left with? So the only non-zero term is on the right-hand side of the equation. So that has to vanish now. What does that mean? So rewrite this a bit nicer. So our alternating tensor double dotted with the stress tensor has to be zero. That's conservation of angular momentum. And when is this satisfied? So is satisfied if our stress tensor Tij is equal to Tji, it's transposed. This product is zero if the stress tensor is symmetric. So if you want, the stress tensor is equal to its transpose. That is the stress tensor. T is symmetric. Or in other words, if the stress tensor T is symmetric, the angular momentum is conserved. So it comes down to a very simple rule, basically, in the conservation of angular momentum. Just leads to the symmetric stress tensor. So for an elastic body now, what does that mean? So for an elastic body, we have Hooke's law. So let's quickly look at Hooke's law. It describes the elasticity and relates the stress to the strain by our elastic tensor C. Now here epsilon, that's strain, is not epsilon hat, which is the Levi-Civita tensor, but it's epsilon the strain. So stress, strain, linearly related by the elastic tensor C. And so for Hooke's law, we see that with a symmetric strain, there is a condition then on the elastic tensor C, on the symmetries of C. And due to the conservation of angular momentum, we see that the stress as well, stress tensor, is symmetric. So what follows are symmetries imposed on the elastic tensor C. So then we haveCijkl equal, one of the symmetries is Cijkl, which would be due to the symmetry of stress, and is equal toCijlk, which would be equal to the symmetry of strain, or due to the symmetry of strain. So you see that the conservation of angular momentum for an elastic medium comes down to a symmetry imposed on the elastic tensor C. So we have, due to the symmetry of strain, which we can define in a symmetric way, and the symmetry of stress, which is imposed by the conservation of angular momentum. We have this symmetry of the elastic tensor. Plus, if you remember, due to the conservation of energy, we have an additional symmetry of the elastic tensor. So there's a third imposed symmetry on the elastic tensor, which leads to the reduction of the number of free parameters that the elastic tensor can have. So the elastic tensor is a fourth order tensor,Cijkl. So the indices go from 1 to 3. So it's 3 times 3 times 3 times 3. So it would be 81 parameters for the tensor. And now with these imposed symmetries, it comes down to only 21 free parameters. And all the others are determined by the symmetries. So we have symmetries due to the conservation of angular momentum, symmetries due to the conservation of energy, and symmetry due to the symmetry of strain. Strain, if you remember, a way to define it in a symmetric way is as this grad S plus its transpose grad S. So that's a symmetric definition of strain. And used most of the time in seismology. In engineering, sometimes you see that strain is only defined as grad S, which isn't necessarily symmetric. It could be a non-symmetric tensor. So then one of these symmetries wouldn't hold for the elastic tensors that we just wrote down above. So this is seismology, where we define strain as a symmetric tensor. And this would often be found in engineering books, where they just simply write the strain as grad of displacement. So sometimes you have to be careful. If you look at an engineering book, mechanical engineering, civil engineering, how they define strain, for example, can be slightly different to what we usually define in seismology. It has to do with these symmetries, basically. Okay, that was just a little excursion. Let me erase it and write down our conservation laws, because now basically we have the 4 conservation laws that we set out at the beginning we want to look at. So in total, almost all in geophysics. Can be described by these 4 conservation laws. So let's quickly write it down. We have the conservation of mass, which boils down to the continuity equation. Is equal to 0. So that's conservation of mass. Then we had linear momentum. So let's use the material derivative expression. It's minus the divergence of the stress equal to the body force. That was linear momentum. Then if we look at angular momentum, it's just that the stress tensor is symmetric. That's angular momentum. Which is conserved. And then if you look at energy, we had rho times the material derivative, the internal energy U, plus the heat flux term, it's a vector, sorry. H is the heat flux vector, equal to this, oops. Let me quickly share again that. Lose connection. Let's see if it comes back. Yes, good. So the stress tensor with the strain rate plus the heat sources, H, and that was conservation of energy. So that's basically all the physical laws that we need to describe almost all in geophysics. Conservation of mass, conservation of linear momentum, conservation of angular momentum, and conservation of energy. Good, and with this I want to finish our little excursion into continuum mechanics and the conservation laws. But I hope it helped you a bit to see where these expressions come from, where the wave equation comes from, the heat equation comes from, and how these conservation laws basically transcend into, for example, symmetries that are imposed. And we look at elastic materials onto the elastic tensor. So do you have any questions so far today? So what we looked at today, conservation of angular momentum. And like with the previous conservation laws, started with basically defining how total angular momentum is defined. And its balance, basically, it's only allowed to change by net torque. The torque can be applied to the volume itself or the surface. And just by rewriting and basically using again the previous conservation laws that we had for mass and linear momentum, it comes down to just this symmetry of the stress tensor. So if the stress tensor is symmetric, then angular momentum is conserved. And if we look at the Hooke's law, That symmetry imposes then symmetry on the elastic tensor, which makes that the elastic tensor at the end only has 21 free parameters. So any elastic body can be described by 21 parameters. And all the rest is determined by its symmetries. So that's then, in short, to summarize all the 4 conservation laws that we looked at with the continuity equation, then the equation of motion, basically, the stress symmetry, and the energy equation. Is this clear so far?
Yeah, the Levi-Civita tensor is used in order to limit some indices in the main tensor, if I get it wrong.
It's mostly used to rewrite the cross product. So you see, in order to write this cross product between two vectors, we can easily use this Levi-Civita tensor. And so this dot product of the Levi-Civita tensor times the stress tensor is then the only product which is left when we look at the conservation of angular momentum. And if you would write it down again with this Levi-Civita tensor, it basically comes down to these symmetries that are then imposed on the stress tensor. So let's see. Just to get it right. So this product of the Levi-Civita tensor with the stress tensor, that's this double dot product. So this would be epsilon ijk, then double dotted with Tij, but in principle, because it's a vector component I that we will look at, jk, so this would be the product. You would have these double sums over j and k. So that's how you would rewrite it. And then you look at this permutation of the index ijk. And then this is then either 1, 0, or -1. And this whole sum is then equal to 0. And so this boils down to the symmetries for the stress tensor. If you would write it out, then you would find that Tij has to be Tji component of the stress tensor. Does that answer the question, Ted?
Yes, kind of, yes. For the time, it's okay.
Good. Good, then what I would do is finish here with the conservation laws, and we have 15 more minutes. I would say let's get started with the stability analysis. We will continue it tomorrow, but let's get a head start now, and then we can finish it tomorrow with the stability analysis. So let's switch the topic a bit and look at how we would analyze the stability of our numerical scheme. So stability analysis. And the exercise was with the diffusion equation, or the heat equation. Of course, that's the same here in this class. So we had here rho density times the specific heat times the time derivative of the temperature, that's T hat, is equal to the spatial derivative of the conductivity times the spatial derivative of temperature. Where we had Fourier's law, basically the heat flux was equal to the negative of the conductivity times the spatial derivative of the temperature. So heat flows in the opposite way, like the gradient of the temperature. This is the heat flux. And in case the conductivity kappa here doesn't depend on position, so it's just a homogeneous medium, we can simplify it a bit. So simplifies to the time derivative of temperature is equal to d, that's now the diffusivity constant, times the second order derivative with respect to x of the temperature. So that's when the conductivity is constant. We can then just define it as the diffusivity is equal to our conductivity divided by rho times the specific heat. C. Conductivity. D, just call it diffusivity coefficient. So for a homogeneous medium, the diffusion equation or heat equation is now very simple. The first order time derivative equal to this constant times the second order spatial derivative, the temperature field. That leads to heat diffusion, basically. That describes heat diffusion. So let us consider now the discretization of that equation. So consider the discretization. Where we discretize space, and now we can write a nodal position xj as being x0 plus j times the grid increment delta x. So delta x is the grid spacing between our grid nodes. Just a regular grid. And the same we can do for time, where we have time step at time n is equal to time t0 plus n times delta t being the time step size. So we discretize space and time, and the temperature field as well becomes discretized. So we can write the temperature at now grid position xj at time tn. Just short is our t hat with the nj notation. That's our notation for a discrete temperature film. Good. So let's look at the schemes that we are using. And from the exercise, what we looked at is the forward scheme, for example, forward difference scheme. In time, so our time derivative now at position j and n is approximated as being this t n plus 1 j minus t at n position j divided by the time step delta t. So that's our forward difference scheme. And we saw last time this is of the order delta t, the first order scheme. Truncation error is linear with the time step size. And the center difference, let's write this as well. So here we need to have it for the spatial derivatives, the second order derivative in this case. So if you look it up, you can write it now in this short notation as Tn j plus 1 minus 2t and j plus t and j minus 1 divided by grid spacing squared. And this is of the order delta x squared. So it's a second order approximation of the differential operator. So is this clear, this notation? So forward difference in time, center difference in space. So our heat or the diffusion equation in a discretized way now becomes what? So let's write that down, the heat equation. The simplified one. I will just write it with the diffusivity. So it becomes our time derivative on the left-hand side. For delta t is equal to this diffusivity constant d times now the spatial derivative, which we can write by this approximation of the central difference scheme, plus t and j minus 1 divided by delta x squared. Good, so what we did basically is rewriting the diffusion equation in a discretized way. So we discretized grid, space, and time, used the finite difference approximations for the derivatives. So the heat equation now becomes this one. And that's the equation that is actually solved now numerically. That's our numerical, if you want, approximation to the true solution. So we solve for the temperature field, the discrete temperature field, T, at every time step n, at every position j. Good, how do we analyze the stability now of that scheme? Well, one way of doing it is by looking at a particular solution, basically. So assume that the solutions, they have a form of like a plane wave. So look for solutions of the form Tij or Tnj can be written as this psi amplitude times e to the ikxj. If you want, xj can be written in these grid space terms, k, j delta x. What this expression is basically a plane wave assumption. So think of k, this is basically your spatial wave number. So it's a real number. Wave number, and psi is an amplitude which can be complex. Could be a complex number. So we basically assume that the temperature field will have this particular form of a plane wave. And so we just stick this assumption into the equation, the discretized heat equation, and then see what is the outcome in terms of constraints on the amplitude term, for example, of psi. If psi, the amplitude, starts increasing with time, it means the time scheme is unstable and the amplitude at some point in time just becomes infinite. So it means the scheme would blow up, basically. So there must be a constraint on the amplitude, psi, that if we look at the time behavior of it, it would stay within bounds, basically. So let's quickly write it down. So the scheme is stable if our amplitude psi remains smaller than 1. That is psi n goes towards 0 and time goes to infinite. Okay. Do we have 2 more minutes? Then we can write it down for this scheme that we have above, the discretized heat equation. So when we would put that in, our plane wave assumption, and then look for the amplitude term psi, it would look something like psi n plus 1 e to the I k j delta x minus psi at n e I k j delta x divided, sorry, sometimes not easy to write on this iPad. So that's the left-hand side is equal to the diffusivity constant times, now it's a bit tedious, but let's write it quickly down. So you see how we would put this into the discretized heat equation. 2 times psi n e I k j delta x plus psi n e I k j minus 1 delta x divided by delta x squared. So these expressions you can simplify a bit. So dividing, for example, by the factor psi n e I k j delta x, and then just using psi as a factor psi n plus 1 over psi n, the ratio of the next time step amplitude divided by the amplitude of this time step n. And this would lead to an expression for psi, which looks like psi is equal to 1 minus 4d delta t divided by delta x squared times sine square of k delta x divided by 2. Which we could rewrite a bit, 1 minus 2 alpha sine square k delta x over 2 and this alpha term is 2d delta t over delta x squared. So from this expression you can see that if psi has to be smaller than 1, it follows that this factor alpha is 2d delta t over delta x squared has to be smaller than 1. Because the sine function or the sine square function cannot be bigger than 1, so this factor alpha has to be smaller than 1 in order to keep psi within the bounds of 1. And by that, basically, it follows this constraint on the time step delta t has to be smaller than delta x squared divided by 2 times the diffusivity constant. So if we choose delta t small enough compared to the grid spacing and the diffusivity constant, to this factor, then the scheme is stable. And this is called conditionally stable. So there is a condition on the time step imposed when we choose a certain grid stepping, so that the space discretization and the material property D determines what time step size we can choose. So if we choose now the delta t too big, the scheme becomes unstable. The solution would blow up time. So this scheme that we set out, when we use a forward difference and center difference scheme for the heat equation or the diffusion equation, so it becomes a conditionally stable scheme. Good. What we do tomorrow is basically we look at the other scheme that we also had. Look at its discretized form and then see if we find a similar condition or not. So we do exactly the same. We use this plane wave assumption, put it into the discretized equation, and then see what follows for psi, basically, for this amplitude term in our assumption. What we see is tomorrow, basically, when we use the different scheme. So we had what was it? Let's see tomorrow. So was it the backward scheme we used? Backward scheme and center scheme?
Yes.
Then it became this implicit scheme, which is unconditionally stable. So there, this condition on psi, that the amplitude factor has always to be smaller than 1, is always satisfied for that scheme. So it's unconditionally stable, which means we can choose any time step size for that scheme. That's the implicit scheme that we also looked at. Good, but let's finish here. We will follow with this part 2 tomorrow and leave it here for now with this conditionally stable scheme. of the heat equation. So in principle, this is already the stability analysis done now for our first example that we had in the homework. We use this forward scheme and center difference scheme to solve the diffusion equation. And we see that these two schemes together, the discretized equation becomes conditionally stable. So there's a condition on how large we can choose the time step size once we have the grid space and the diffusivity determined at the beginning. Good. Do you have questions, remarks? Anything?
I have a question.
Yeah, Kali?
Okay. I just wondering how should we call the alpha here? Is it a stability factor or instability factor or? Yeah.
No, here alpha, that's just this this coefficient that comes out when we rewrite the so the discretized version. When we put this in, then we just have these expressions here.
Okay.
And in order to simplify a bit to see what the condition would be in order to feel that it is smaller than 1, we can just rewrite it a little bit, something like this here, in this form. And alpha just makes it a bit more convenient to see that at the end it depends on this coefficient alpha. Because the sine square will always be within plus minus 1, or between 0 and 1 actually. And so in order to go beyond 1, it depends on what this factor alpha will be. It's just a little helper to see a bit better what this condition will be that follows for the time step. There's no particular name for that. So it's a bit tedious to write it out to get to these expressions. But the main point here, basically, when you go through all these derivations, is that you have this condition on the time step size.
Okay.
Is that good, sir?
Okay, thank you, Professor.
So if everyone is fine, then we see each other tomorrow again, same time. And please send me your preferences for Sunday, Thursday, or Wednesday morning, Thursday morning. So we can discuss it tomorrow. Decide then by tomorrow what we want to do. Is it okay? Just send me a quick email stating which one you prefer. Good. And then if you can finish up the homework by this evening, so then I can quickly look at it for tomorrow as well. Is it okay?
The first point, right?
Yes, homework 1. Which basically makes this, it solves the heat equation. Good. So let me stop sharing here. Then I wish you good day, good night, and see you tomorrow.
See you. Bye.
Enjoy your
Thanks.
day. Bye, everyone.
Bye.